All right, everybody online can hear me?
Yeah.
Okey-dokey. Let's see. And I do have the bugs worked out in the Proc file system. And we'll talk a little bit more about that today. And I'm going to talk about sequence files first, since that is kind of the newer way things work. So last time, and actually I'm going to jump between slides a little bit here just to order them. Last time we talked about interprocess communication because we were giving a high level overview of kind of the purpose of the Proc file system, right? So what we've looked at more recently is we've looked at the device file system. Specifically, we looked at character devices, right? As opposed to block devices, which I think we mentioned block devices, just kind of said those are like your hard drives and that kind of stuff. Okay, but character devices are what we actually wrote some code for, where it's almost like a pseudo, almost like a fake device that we can create that kind of feeds information. And actually, there's some interesting examples of that. Like there's something called dev null. Let me just see where. So let me just talk about it here, and then we'll bounce between some stuff. And then I'll come back and talk about sequence files. All right, so dev versus proc file system. So last time we talked about the proc file system kind of being each file in there is associated with a single process running on the computer. So that's a computer program running on the computer. Previously, we talked about the dev file system, specifically character devices, but we also mentioned the idea of block devices. And these are files associated with, let's say physical hardware for this comparison here. So on one hand, we're talking about a running program. On the other hand, we're talking about physical hardware. All right, that's the difference between these two file systems. But again, since it's a POSIX-based operating system, everything is represented as a file. And these files just kind of have a kind of special, they're kind of special node types that allow the kernel to use these files in some different ways. Devices in Linux is devices, any piece of equipment, yada, yada, yada. So keyboards, hard drives, things like that. So we mentioned this out loud, but I put a slide in here for character versus block devices. Character devices deal with I/O on a character by character basis. So obvious example might be a keyboard. So the character device acts as a conduit between a physical piece of hardware like a keyboard and a whoever is interested in reading from that file. Could be, our little examples have us doing like a cat from the command line, something like that. Otherwise, you could have another program that opened up something from the dev file system and read from or wrote to, that kind of thing. So block devices, use your hard drives, that kind of stuff. Inside of the dev file system, if I just go over here and open up my terminal, and I'll just go to /cd/dev. We should see we have here's block devices, here's CD-ROM, here's char devices. So, you have some organization of where these different devices might live. Now, one interesting thing, let me actually try to do it from here, cat/dev0 before I talk about it. cat/dev random. There we go. All right, so there's some interesting devices that are out there that are kind of created as part of the operating system. And they're not that important for us from like hey, you don't have to go memorize these. But there is a dev random, which you can use to just provide you random data, random bits. Now, How that random data is generated isn't our problem. That's something the kernel does. It's probably collecting data from different sources and just funnels it all to this place in a jumbled up order. So the idea is if you have a program that kind of needs something that's just, I just need random junk to initialize something or something like that, you know, there is a device called /dev/random that will provide that for you. There's another one called dev zeros. There's another one called dev null. So dev null is kind of like a waste bucket. So let's say you have a bunch of error messages that are coming to the screen. You can redirect standard error to dev null and basically saying, I don't care about the existence of this. And you don't have to worry about emptying it. So dev null is like the void. Okay, you know, it's just send stuff to that place. So these are just kind of, they've been around for a long time. Typically, you'll find them in the dev file system. Just a thing. So in any case, these devices are organized in some sort of interesting way. Okay, so when we talk about what's in the dev file system, we're talking about communicating with hardware. Let's just say mostly. We can find examples in there where it's kind of a fake-C type situation, but mostly it's communicating with hardware, where the /proc file system is communicating with running processes. Okay, so proc file system, at any given time, Linux will have many processes running at once, such as Windows managers, email clients, web browsers. They'll be visible to the end user. We saw them through the top command. Servers, helper processes, servers that are running in the background are often called daemons, D-A-E-M-O-N-S. You know, they might not be immediately visible, but because they run in the background, handling tasks that don't require the user's interaction. I think I've run I think I ran AF that showed you all running processes. So you'd see things that even aren't necessarily obvious. Okay, so that's the differentiating thing between these two different things. One is communicating with processors, and we talked about inter-process communication last time. The other one is communicating with devices. Okay, so now let's talk about this idea of a sequence file. All right, so modern programming uses global networks as a source of reference information, in particular a source of patterns for solving unknown or little known problems for a specific programmer. Such an approach saves a lot of time and often gives quite qualitative results. However, the solution laid out in the network, although usually correct, do not always take into account all the subtleties of solving a problem, which leads to the appearance in the source code of sections that usually work correctly, but under not quite standard circumstances become sources of unpleasant surprises. So we're going to be looking at this from an efficiency perspective. So consider the topic of using sequence files in the Linux kernel. Such files are considered to be the most convenient mechanism for printing from the kernel mode, but in practice, using them correctly is much more difficult than you would think. And we're going to see this from an example. And this next thing kind of talks about it, but I'm going to talk about the high level. It's natural to use sequence files. The most common situation is to create your own file, maybe in the proc file systems like we're doing. And then by reading the files in the system, you can get a variety of information about the equipment used, its drivers, RAM, processes, things like that. Keep in mind, this is probably coming from a process, which might be talking to a driver, might be talking to a device, something like that. When we read and write from sequence files, which you can kind of think of, we've been talking in here about these things called buffers, right? Where a buffer is a collection of data that kind of has a fixed size. Now, the more modern approach to buffers is something called streams, where streams provide data until they don't provide data, all right? So sequence files kind of live in the middle. Sequence files are like a file connection to a stream. I guess that's a reasonable way of putting it, where you can keep reading or writing to a sequence file, well, reading is the better example, as long as there's data available. Now, historically, well, for us historically, which is just several weeks, we've looked at buffers where maybe we had a buffer that was 1,024 bytes. That was the maximum chunk we could read at one time, but we didn't necessarily always fill that buffer up with information. So we would say that the most efficient way of reading from any kind of file would be to read from read it 1024 bytes in its entirety, right? So literally we have a bucket that can hold 1020. If you're filling a swimming pool with water, one bucket at a time. Ideally, you'd want to, when you make the trip to fill the bucket with water, you want to fill the bucket, right? And then dump it in the pool. You don't want to put a teaspoon of water in the bucket, take it back, dump it in, take it back, get another teaspoon, dump it in, so on and so forth. That would be very tedious, right? Now, the funny thing is that the way we typically work with our modern day streams in our operating systems is the teaspoon method. That is to say, we go back and we get one character at a time. The difference is, and we've kind of seen this even though we haven't been on the receiving end of dealing with the consequences of this, but if you have something that reads from a file and you have a bucket that could read up to 1024 bytes, yet a lot of times the function returns something like the number of bytes read, and I can show you an example of that. Character device driver have that in there? Where's our read? Yeah, here's our read. So this is what we were filling up, but what it returned was how much did I actually read in? How much did I put into that buffer? You know, buffer gave me a bucket to fill, but how much did I actually put in there? All right, so this is a common cadence for some of these, even the newer version of some of these older libraries. Let's see where I was going with that. So with that in mind, we can try to be as efficient as possible as a computer programmer and say, I'm always going to just basically sit in this read file until I fill up my buffer, but we don't know how quickly the data is going to get to us, right? If you're reading from a local file, you can kind of make the assumption the data is going to fill up pretty quick because that's a very direct connection. But if you're opening up a stream over the internet, we don't know how fast it's going to download or you know, whether or not we're going to have you know, dropped packets or something. So we have no guarantee how quickly we're going to get data. So we kind of have to make two choices. Do we try to get data in the most efficient way possible, where efficiency means minimize the number of times we read? So in our example of filling a swimming pool, which is more efficient? Do we minimize the number of trips we have to make to the faucet to fill the bucket? Or do we minimize the amount of downtime between, do I want to advertise it as downtime? Because it says you could make the argument that trips to the sink will actually also be downtime. If we're doing it 1 teaspoon at a time, provided we can get some sort of cadence going, you know, maybe we have a little supply chain type thing where people are passing the bucket along, we can keep a very steady stream potentially of teaspoon-sized dumps into the pool. All right, so we can say that's kind of like serial communication. All right, it's not very efficient. You know, we're kind of handing one spoon to, you know, we have a stream, you know, line of people, that's the stream, and we have one spoon constantly in front of another being delivered, where we're only ever filling up spoons, we're only filling up water 1 spoon at a time, which would be 1 call to the read function. All right, so do we consider it to be efficient by having a minimal number of calls to the read function, or do we consider it efficient to make sure that we always have data, even if it's a small bit of data? The answer is it depends, right? You know, we can't necessarily make a choice of which one's easier or harder from a which would we desire perspective. But now from a programmer's perspective, so for us in here as systems programmers, we want to think about which would we prefer. Do we want to write algorithms to try to maximize the efficiency of reading from a device, where we kind of hang out there and read our 1024 bytes, then return and come back and pick up where we left off and so on and so forth? you know, where you could maybe do that, especially if you just make the assumption that the data is always going to be available, right? We don't kind of throw out this idea that there could be a delay in data. So data is always available. We can say we're going to write some code that will fill up the entire bucket of water. We'll go and dump it, then we'll come back and we'll fill it up from where we left off. You know, the idea is we have to turn the faucet off, then we come back, we turn the faucet back on, so we technically get the next molecule of water for bringing it back to the pool. We can say that really that would be the most efficient for time and everything, but there is also quite a bit of overhead with that from a programmer's perspective. Now, the flip side is computer programmers could also operate from the perspective that computers are really, really fast and we don't care how much extra work they have to do as long as it's not our problem, right? So we can say, fine, filling up that swimming pool 1 tablespoon at a time or 1 teaspoon at a time, whatever I said, seems completely ridiculous from a human being's perspective. If it's a computer we're telling what to do, what do we care, right? I mean, you know, we have one of these little robotic vacuums at my house and the thing takes forever to vacuum the house, but who cares? We're not there. You know, it goes under the beds, all this stuff. Sometimes it gets stuck behind doors, finally finds its way out. You'll find the carpet for the rug from like the shower, outside the shower, you'll find that drug into the kitchen. It just brought it with you. It's like having a dog. You know, so it does these things, but you know, we don't care that it's inefficient because we're not in charge of it. It just does it autonomously and goes and does its thing. All right, so from a programmer's perspective, we can say, well, I can write code that's going to do all this extra heavy lifting, manipulating the data, keeping track of where we left off, stuff like that. Or you know what? I can just say, I'm going to read in 1 character at a time, whether you have more to give me than that or not. I'll read in a character, I'll write it out. I'll read in another one, I'll write it out. Oh, you got more to give me? I don't care. Give me 1. Write it out. Write it out. That would be the more convenient way for a computer programmer to write that. Make some sense? Okay. So generally speaking, when we see examples, we're usually going to be reading 1 byte at a time, even though we can say that that's probably not the ideal solution, but that is the solution that leverages the power of computing more so than the, I don't know, us respecting the computer's feelings or something along those lines. Now, what is interesting about this is we can sit here and say, well, that seems really inefficient to fill a swimming pool up with, you know, 1 teaspoon at a time, but eventually you get the thing full, right? Same thing is true here where, well, it's kind of extra bad in this case. When we think about IO, and you've probably seen me demonstrate this in a different class, if we write a program that counts from like 1 to 1,000,000, and all we're doing is counting, it'll count 1 to 1,000,000, and then I do a single print at the end, it prints out the 1,000,000 really quickly. But if I take that same program, I introduce a print statement in the middle where I'm asking it to print out the current count 1,000,000 times. That program runs way, way, way slower because doing IO is expensive. Reading and writing is an expensive endeavor because it requires you to leave the CPU, do what's called a context switch, to go and do IO operations. So again, if we need something to be really, really, really fast, we probably want to limit the number of IO operations we do. If we don't really care and it's just about the data we're going to get, probably don't limit and just write your character by character type of setup. All right, so before we go any farther on the theory side of this, let's look at some updated code here. So we're going to be using sequence files, and we'll talk more about that when we get into it. So similar to what we did before, we're still building a module. We're just building a module around the proc file system instead of the device file system. Okay, we're going to be using specific kinds of files for reading and writing, which for us right now, let's just assume that these are modern serializable files that allow reading and writing 1 byte at a time. All right, so now, before we jump into this, let me just show you a quick picture. So this is kind of let me just make sure I didn't skip anything here. So this is what we just talked about, the good versus common programming practice thing. So here's kind of our sequence file flowchart when we're working with sequence files. That is when the sequence file is the resource that we are letting our proc file system leverage. We have a starting point. So this is kind of our flow chart for this guy. So we have our starting point, and one thing we might do is we might show something to the user, which then goes through the kernel, right? Now, if we're done, let's call this 1 byte. We're going to show 1 byte to the user, 1 character to the user. So that's going to go through the kernel, and we're going to write 1 character out to the screen. All right. From there, we can either go to the next one, or we can, I guess, potentially can have a buffer overflow where you've run out of your space if you fill up your buffer 1 character at a time instead of overwriting it. But in any case, you can just kind of say, if you're done showing stuff to the user, go to the stop state, which then goes back up and it's ready to run again. Similarly, if you're showing 1 character, goes to the OS to show it, goes to next, show another one, yada, yada, yada. And we'll see the show function here in a few minutes. I'm just connecting these dots and we'll look at the code. So one of the functions we should see related to sequence files is a function called show. Another one is a function called stop. Another one is a function called next. Another one is a function called start. Okay? We should have these multiple functions that play out this ecosystem here. Okay, so we can get into this nice little loop here where we're showing you 1 character at a time over and over and over again until we finally run out of crap to read, and then we stop and bounce back. Similarly, we could start, and if we got nothing to show, we stop, and that's the end. Similarly, we can, let's see, that's the only 2 starting cases. Can I go from, when you go to read in next, if there's nothing next to read, you go to the stop state and go back to the beginning. All right, so this would kind of be an error state right here. If you tried to do something and something bad happened, you would error out, go to a stop state and go back up. Okay, but in any case, we have these 4 functions, and let's look at these 4 functions in practice. So here's our show function. This is going to be pretty similar to what we did in our modules before. Okay, so with our read and our write, well, we didn't implement write, but we saw how write could have been implemented. All right, so we have our show function. All show is going to do is it's going to printf to a sequence file. So we got a special function that knows how to read and write things. Printf is a write thing. So it knows how to write to sequence files. Whatever best practices is for that. All right, so again, as human beings, we can say, we want to be as efficient as possible. As programmers, we can say, well, let's just get it done. As modern day systems developers, we can say, you want me to write something to this sequence file? No problem. This is what I want to write. Do it whatever way you think is best. We're just passing the buck because this is something that already exists. This function is a tool for writing stuff to a sequence file, and it's going to do it in whatever way makes the most sense. The sequence file is what gets passed in right here. Okay, so hello proc show writes to a sequence file, hello proc. That's all that guy does. All right, when we first open a sequence file, we'll open it a single time, the file, and we'll actually call show. Okay, so those 2 kind of work. We open the file and show. So those 2 happen as like sequences to each other. You could probably connect this with the start function from this previous chart. This is the open. It's when we start. All right, we have our proc file ops. All right, so the name of the open function is called hello open, hello proc open. The name of the read is sequence read. The name of the something called lseek, which lets you look stuff up at different points in the file, so you can kind of read forward, read back, is called sequence lseek. Now these guys, these are already written for us. So reading from a sequence file, we could write our own. and have it follow a whatever the naming convention or the header convention here is for that particular function, and write our own version of that. But instead, this guy's saying, hey, look, we're going to do the plain Jane read from a sequence file, whatever that means. We're going to do the plain Jane seek from a single file. To release it, we'll do single release. Here's our module stuff. So this is our initializing our proc module. So no different than we did before, except before we created a device. Now we're creating something in the proc file system. This is where we were having an error last time, where it was using an older style version of the proc library. So the newer style has a function called proc create. This guy lives in Linux /procfs. So proc create takes in the name of the file you're creating. Let's see, I don't know what the second parameter is. If I hover over this, will it tell me? I don't know what these two parameters are. But this guy is our file operations for hello proc, which we defined right here. So this effectively like hooks up the wires. When we create this special file inside of the proc file system, this would be /proc/hello proc, it's going to link it up to this function for opening, which then passes it off to the show. Okay, so we do a single open. Here's the name of the file. We call that function. And that's going to print to the sequence file hello. So this will create that file when we first install this module. When we uninstall this module, we will remove this proc entry. So we'll remove that guy from the proc file system. So this is our way into the proc file system. This is our way out of the proc file system in terms of creating a special, I bet you this is the process ID. By putting a 0 there as the process ID, it probably creates a new file and doesn't link it to an actual process or an existing process. All right, so this guy will remove it from there. So this is our way of creating a file in the proc file system or removing a file from the proc file system. Down here, we talked about this module license not required. It'll give you a warning or something. But then we associate with our module, what function do we call when a module is being init, which is what gets called when we call insmod for this guy. Similarly, when we call rmmod, what function gets called to clean up the module. Okay, so this is an example of a proc file system program that's reading from this guy. So I come out here, let's go back into here. So I'll go ahead and if you just do more on make, you see that this guy uses this procfs1.0, same make file we had before. So if I do a make all or just type in make, it'll do all the building stuff like this. So I end up with a procfs1.ko. That's my kernel module. Installing it, we do sudo insmod procfs.ko. Ask me for my password. Ask me for my password more better. Most bestest. Ask me for my password most bestest. All right, so now this guy should be installed. So I should be able to now, if I open the thing for reading, that's going to be me trying to read from it, then it's going to show to me. So I can do cat/proc/hello proc. So we see that guy was created there, and there's my hello proc. And nothing keeps me from doing the same thing we did before with a static library or a static count where it says, I already told you so many times. So nothing's different there. It has more to do with whether we're looking at a communication channel between processes, or we're looking at a communication channel between a program and a device. Okay, So there's us, and I don't think we have a write to it. So if I echo woot to /proc/hello proc, I might need to sudo that. We'll do that. Yeah, I don't think we've opened it up for writing. And the owner would be the module itself, so we'd have to write to it from within the kernel. And sudo doesn't let you do that. I'm trying to give you a good example of when you would. The question then comes down to, how does this file get its data? Right now we have our proc show and the data is hard-coded data, right? But this guy is running inside of kernel space. So if there was something else, if there was another program that was running, and that program was writing to a file or another kind of inter-process communication, we could read from that and write to this guy because this guy's running inside of kernel space. So we're just writing out a string literal right here, right? We're saying, hello, proc, every single time. We're not getting any sort of dynamic data or anything like that. But what if every single time we called proc show, it read the next byte from some source? Maybe it's reading in from dev random, for example, reads in a byte from dev random and writes it out. This gives us access to read from those things since the read is coming from the context of kernel space. The module here lives in kernel space. Anything that we do inside of here happens in kernel space. That make sense? All right, so I'm trying to come up with an example of when we want to write to a proc directly. I don't think we would. Writing would always happen from another process, which isn't necessarily, so that's a good picture. I think that's the best way to show this. When do we write to a proc file? So we might say here that it might not make sense for us to write directly to a proc file, but a module lives in kernel space. A running process lives in either kernel or user space. There exists, just say, communication channels for user space based applications to reach kernel space. All right, so now let's look at a picture so we understand this, because I labeled some of these things last time. We talked about semaphores and signals and some of these other inter-process communication IPC things. So if I draw a picture, hide this. So we have kernel space. And the proc file system lives inside of kernel space. Put this as a, this is proc fs. And then I'm going to create a user space. All right, and we'll go ahead and we'll create P1, P2, and let's just say that P3 here happens to be like a kernel, something running as part of the operating system, part of the microkernel, probably a running module, since what we're dealing with here is a microkernel. So the kernel itself is self-contained, and then we have kind of kernel level applications that are running to serve the kernel when those exist in the form factor of a module. All right, so more than likely what we're doing here is we're talking about the module subsystem. With a process living on top of that in the form of a module. The way that process was launched was as a module. Okay. So an issue here is how does, let me move this down some. This process could potentially communicate with the proc file system directly. It would have the ability to do that because it's behind the kernel, it's in kernel space, it's behind the firewall, if you will. All this stuff is happening over here on the other side, on the side of the fence where you're allowed to do super user stuff. Okay, but process P1 and P2 might want to talk to each other. So how does P1 send a message to P2? Well, if you hard coded some values, you might be able to, well, actually we have a couple, modernly we have a couple different ways we can do this. We can actually leave the operating system. So one thing we could do we can maybe go to the cloud. And maybe up in the cloud, we have like a database. It could be Firebase or something like that, some kind of database up in the cloud. And P1 reads or writes the DB, P2 reads or writes to the DB over the internet, so they can actually both communicate with each other using this complete foreign object, right? It's not even on the same system. They're effectively bypassing all the rules that are in here. As long as this computer they're living on here has internet access, they can just say, look, I'm going to share stuff between these two processes, and I don't want to play the stupid game. Now, we would say that this connection, the connection between P1 and DB and P2 and DB is slow. However fast your internet is, even if you have really, really fast internet, it's probably going to be slower than your local file system. All right, so you're trading off speed for maybe convenience. Now, is there an argument when you still would do something like this? When might this make sense to have two processes running on a single machine right to something in the cloud to communicate with each other? Go ahead. Yeah. So what if you have some processes, maybe it's the same P1 and P2, you know, the same, maybe it's from you know, some program, software program that you launch, and you launch it on two different computers. Both of those software programs, the two processes associated with it, need to share the same data. Now you do need to have it offsite somewhere because they both need to access that same singleton that lives outside of the single computer, right? So it's not like this is a dumb idea, but again, it comes down to what's the right tool for the job. All right. So another option is we could create a file, local FS, instead of our local file system. Let's call this my file. So both of these guys could read and write from this local file here. Pros and cons of that, in your view? Well, what's one pro? Possibly, well, certainly faster than the internet one, probably. One pro is we don't have to screw with the rules of kernel space. But we also, the side effect then is we also don't get some of the benefits of kernel space. Certain things can happen in kernel space that would not be allowed in user space. And this comes down to something called atomic operations, among other things, but atomic operations are probably the best example, or the most relevant example to what we're talking about here. But if we just think about, hey, we're an old school programmer, we got two processes that need to communicate with each other somehow, what can you do? You can say, oh, yeah, I'm just going to create another file that both of these guys can read and write from. It's going to be maybe in the same directory, someplace publicly readable, or I made the file 777 so everybody can read, write, execute. It doesn't matter. It's a completely public file, and I'm going to throw stuff in there for these guys to share. So don't have to go through the security hoops. At the same time, you also now don't have any security. In order for that file to be writable from those two processes, it needs to have it has to have write permissions from whoever the owner of the running process is, or at least the group that the process is running as. Okay, so the permissions are probably going to be fairly open for that file. So that means somebody else who maybe logs into the computer could go to wherever that file is, some public file system somewhere, and read whatever's in it. Maybe that's useful, maybe it's not, right? You know, it kind of depends on the nature of the data. But you also are going to now have to invent your own kind of communication protocol. You're going to have to decide, how do P1 and P2 talk to each other through this file? Because this file doesn't have rules associated with it, right? You know, we think about this in real life where we have like walkie-talkies. I think I mentioned this last time, where you say something and then you say over, and was that in here? I mentioned that? Okay, yeah. So, you know, we can invent a protocol that makes communication over a custom channel make it make sense, but we'd have to do the same thing here. How do we know that P1 and P2, how do we know that one of the guys can write to the file if the other guy might be in the middle of writing to the file, something like that? We're gonna have some level of oversight for a file. Kernel, well, the operating system, this could be done at the actual compiled into the kernel level, and some of it will be. Some of it could be delivered through a module of some kind. But it provides a set of tools, a set of APIs that allow two processes to talk to each other with various abilities through system calls like signals, like semaphores. So for example, if we were looking at this from a semaphore perspective, we might say that both P1 and P2 share a semaphore. And the semaphore is effectively the bouncer to this file. And so we're going to say in this example, must increment to write to my file. So that means P1 and P2, in order to get to my file for writing, they have to go through this bouncer. And this bouncer is written what's called atomically. So it's written in such a way that only one of them can actually increment or decrement that semaphore at the same time. So as long as the semaphore is currently a 0, when you read from it, if it currently shows a 0, that means the resource is available. When you increment that semaphore, since right now we have one resource that we're protecting. So we have a bouncer that's standing at one door, keeping people from coming in. All right, so once somebody starts going through the door, nobody else can go through the door. It's not like a second door they can go through. You think about this like at McDonald's, you walk in and there might be 3 registers open. You kind of get in the one that has the shortest line or whatever. Well, in this case, there's one register. Everybody's rushing in at the lunch rush, and only one person can get that resource at a time, and it's whoever grabs it first. In real life, we might say, well, what if 2 people run up to the register at the exact same time and start ordering? Well, maybe you go down to the slow motion tape and see who actually got there first, just like they do in like the Olympics or something. But realistically, there might be a thing where two people could try to get to the register at the same time. What atomic operations at the operating system level say is they say both things can't get this resource at the same time, because that increment operation happens atomically, which means it happens as if it occurred in exactly one CPU cycle. Atomic operations. Operations that occur as if they occurred in exactly one CPU cycle. Basically happens in a single non-divisible instruction. Can't be interrupted. If it didn't happen atomically, and let's say it took 3 instructions to accomplish the thing we wanted, you go to the memory location, you increment the value, you write the value back, let's say something like that. Even though that all happens pretty fast, and we can say that it's even unlikely that 2 processes would get CPU time at the same time, well, close enough to each other where that could happen out of order, where one person opens it, changes the value, but before they write back to it, somebody else opens it, changes the value and writes back, and then the first person writes back. Now you've messed up the data because 2 people were accessing the same resource at the same time. Atomic operations, whether they're actually atomic or not, happen as if they are atomic. It's a non-divisible instruction that you can't jump in the middle and do it. When you increment a semaphore, it's a special system call that will make that special integer go up by 1. And nobody else can be doing that at the same time as you are. If they tried to, they'd be locked out. Bouncers dealing with the person currently going through the door. When they're done with that resource and they come out, that's when they release the semaphore. They decrement the semaphore, which would then let the person who's banging on the door on the other side, who keeps checking back, lets them finally get in. All right, so these are atomic operations. So most interprocess communication, when we're talking about these things, since they are either sharing a resource or providing some mechanism for the 2 processes to directly send data to each other, because it might not be sharing a resource. It might be effectively giving them a walkie-talkie, right? Process 1 needs to be able to kind of know what process 2 is up to, or if we think about this like an old school merge sort type thing, where you could write merge sort in a multi-threaded way, but what if the predecessor to threads would have been full-blown processes? So you would have the parent process that starts spawning off child processes, which is a system called fork, which we'll look at in here as well. You've seen it with GitHub, right? Where you can fork a repository, which creates a duplicate of it. All right. So with a system called like fork, you can have maybe for a merge sort, you have the parent process, and then you have 2 child processes, one for doing the left half and one for doing the right half. Well, those 2 child processes need to be able to report back to the parent when they're done sorting their halves, so that the parent can finally go and merge the final step together. Make sense? All right, so we need to have various ways for processes to communicate with each other. And some of these things can happen in user space. Some of these things will happen in kernel space. And the reason why some of it has to happen in kernel space is because of the nature of the things you can do in kernel space. It's dangerous to be in kernel space, but at the same time, it also allows you to accomplish things like atomic operations in kernel space. All right, that makes some sense? All right, so next time what we're going to try to do is we're going to try to bring these 2 sides together and have 2 processes communicating with each other through the Proc file system in like a practical way. Maybe we'll have, I don't know what I'll have them do yet, count back and forth. Maybe one will say 1, the other one will say 2, the other one will say 3, but they kind of wait for each other. I'll come up with some stupid example, but we want to see us actually utilizing that Proc file system as a potential way of inter-process communication. Okay. Questions, comments, concerns, bribes? And I'll push the current code up there in case you want to experiment with it or anything. It's should be all working right now, but I'll be adding to it. So I'll see everybody on Wednesday.